And by the way, okay, today is February 22nd, 2023. Okay, Wednesday. And let me, okay, today, what we're going to do today? Today, you know, we're going to cover some of the lecture material, right? That's what we're going to do that today. Two, we're also going to review the work that you did last lab. So because of that, I want you, for this reason, I want you to upload the spreadsheet you have, to your group folder. I do that only for the first lab because some of you don't understand very well how you do the lab. So I do that for the first lab, and then the rest, the other labs, we just move on with the labs. Okay, if you look at the syllabus, here you go, 22nd, right? Chapters 18, 19, lab 1. Lab 1 covers electric potential and electric field as well. And I'm going to review what you did in the previous lab. And because of that, I need you to upload your spreadsheet to your group folder. I'm not going to grade it. I'm just going to, review every spreadsheet and make sure that you did everything right. And then next week, we get into lab number 2, okay? I need it. Go. So we're going to cover some of the lecture material. We're also going to review the work that you did last lab. Okay, please upload, right? Please upload the spreadsheet, lab 1 spreadsheet, lab 1 spreadsheet to your group folder. And then next week, you prepare the final report for lab 1, which will be due next week, which will be due March 1st, okay? So going back here. Okay, so here you go. The final report on lab 1 is going to be due on March 1st. Okay, but again, I need you, please upload your spreadsheet to your group folder. Yeah, and remember, it's just one spreadsheet per group, right? One spreadsheet per group. We're clear? Is that clear?
All clear.
Okay, thank you. Let's see. This is here. And this one. Let's see. Process law, okay. What I want to do, I want to continue what I was doing in the last, and let's see. So we will spend the first hour. We will spend the first hour covering the lecture material, okay, and the rest I will review your spreadsheet. Okay, that and by the way, you can see this screen, right? Let me scrolling up and down. Okay, good. Okay, so let's finish. Let us finish Gauss's law. Gauss's law. Okay, last time, what did we do? Last time I formulated, I formulated Gauss's law. I formulated Gauss's law and solved it and used it, not solved it, used it for the case. Which one did we use? We did, let's see. Point charge, right? Well, let's call this one here example 1. First one is that of point charge. And this should be example 2. Okay. Example 2. Example 2, okay? So, your book also has 4-point charge, and how is the Gauss's law formulated, right? Use it to get the electric field of the point charge and the spherical shell charge, and a spherical and a spherically charged shell. Okay, and Gauss's law is the following. Here you go. It's going to be the electric flux, Phi. Okay. That's I'm using the same notation of the book. Okay, and what else? Should be Q enclosed divided by that constant, the electric constant that we call epsilon naught, which, by the way, is related to that more familiar constant, the K constant, okay, by this relation here. So 1 divided by epsilon naught is going to be given by 4 pi K. Okay, dielectric constant and the factor K. That goes in that formula for the force, okay? The constant, this constant K is the same that shows up at the shows up in the equation for the force, for the electric force in Coulomb's law. Okay, So, and then how do you write the electric flux, right? The electric flux. How do you write the electric flux? Okay, the electric flux. Electric flux depends on the geometry used to solve your problem. Okay. So let me give an example. Let me show you an example here. The simplest electric flux that you're going to see out there is going to be that of a uniform electric field. Okay, here you go. Uniform electric field. I don't need that anymore. And I don't need that. You know, traversing a plane. A plane just like this one, plane of size A and B. Okay, that's the simplest electric field, that electric flux that I'm going to see in there. That's the simplest electric flux that you're going to see out there. And so what's that going to be in this specific case? Okay, the electric flux is going to be given in the case of this plane, you know, flat plane. You have an area vector that can be drawn towards the left. And in this case, the area vector is parallel to the electric field. Okay, so here you go. Electric flux is going to be given by E area vector times the cosine between the two vectors, the electric field and the area vector. Okay, so here you go. The electric field and the area vector. That's how we define the electric flux. For a plane perpendicular to the electric field, the area vector of the plane will be parallel to the electric field. And the above formula reduces to, okay, here you go, E times A. Okay, let me write it down here too. The easiest problem, right? Involving the electric flux refers to that of a uniform electric field going through the plane, an imaginary plane, okay? That is perpendicular to the field, that is perpendicular to the field. Okay. If we go ahead and let's see. It's not, I don't want this one. If we put this plane now parallel to the electric field, okay, that was the plane that we initially had, right? Let's see here. I'm mixing up here. Here you go. That's the one that I want. Here you go. Here's the plane, right? If I want to, if I want to simplify the drawing of this plane, all I do is, put the plane as represent the plane as a line perpendicular to the field. In this specific case, the electric flux is going to be EA, just the electric field times A. If the plane is parallel, the plane itself is parallel to the field, the vector area is going to be perpendicular. Okay, and the electric flux is going to be 0. Make sense? The area, here you go, perpendicular to the field makes an angle of 90 degrees. You put those two vectors tail to tail, you have a 90-degree angle, and you just write down the electric flux. In this case, you go for the plane, for a plane, not the plane, for a plane parallel to the E field, then the electric flux is 0, because the area vector of the plane will be perpendicular to the field. Okay. Another example, a third example, here you go, is this one here. Now the area vector here is making an angle phi with the field, and the electric flux will have this formula here, which is the genetic formula. Okay, that's the case for for the case of the area vector making an arbitrary angle with the field. Okay, the electric flux, the flux will be given by the original definition, or arbitrary, making an arbitrary angle phi with the field. Okay, that's what you have to know about the electric flux. Okay, and then we started. We solved for some problems that had symmetry, that had spherical symmetry, like this one here. Okay, I want to find out the electric field of this point charge using Gauss's law. What do? I draw an imaginary surface, which is the Gaussian surface. Doesn't matter if the surface is here or further down. The surface is further here or further down. In this specific case, for this specific geometry, the area vector will always be parallel to the electric field, right? And we did this one here in the previous class. The flux is going to be EA, because the electric field is always parallel to the area vector. And the Q enclosed is going to be this charge here that I call Q in my solution, right? The area of the Gaussian, here is the area of the Gaussian surface, okay? The area of the Gaussian surface is 4 pi r squared. And that's what I did here. And you get that KQ over r squared. That's one example for the point charge. The other example for a spherical shell, like this one. You saw that. You go. And I want to solve the field both inside and outside the spherical shell. What do? This problem has spherical symmetry. We can draw a Gaussian surface on the inside of the sphere. The sphere has radius r. But notice that there is no charge here inside. Consequently, the electrical flux through this sphere is going to be 0. Q enclosed is 0. Okay, here you go. So the electric field on the inside is going to be 0. But on the outside is not going to be 0. Because on the outside, if we draw our Gaussian surface outside the sphere, we are going to get some charges in there, which is going to be, and then this problem reduces to that of point charge. It just happened that it has a different symmetry. Here you go, KQ over R squared. And then that's how we represent the electric field, you know, inside and outside the sphere. There are other types of geometry that you can, that you can solve this problem as well. Okay. We have this example of the shell is example 15 in the book, by the way. And let's see, example 16. Let's see. In the example 16, we can also do the case, for example, 16. I will do that in a different way, okay? The book is doing one way. I prefer to do it in a different way. Okay, and so another example. Oops. Example 3. Example 3. You know, find the electric field of a very large flat, very large charged flat plate. Of a flat plate, okay, of a very large flat plate of area A and charge Q. Actually, we do not need the area of this guy. Okay. Of charge Q. Of uniform charge distribution and net charge Q. That's the best way of representing that. Okay. The book did 2 plates. I'm going to do only a single plate. That's better this way. Okay, solution. Let's see. I need an area charge of net charge Q. Yeah, we need the area here and area A. It's better if you give the area A because there's a simplification to our final result. Okay, and don't forget we need to make a drawing of the situation. Okay, so here you go. Uniformly charged cylinder. Here you go. That's the one we want to do. Infinitely large planar surface. So we have something like that. If you work out this problem in a qualitative way, okay, we can find out that the net field of something like that is going to be to the right. Okay, if this plate is very large, you know, those y components tend to cancel out, and well, the only thing that's left is going to be a field to the right. Okay, so something like that. It's going to be to the right. On the right side is going to be to the right. The volume on the left side is going to be to the left. That's how the electric field should look like. And by the way, that was exactly what you did in the previous example, right? In the previous lab, not example, in the previous lab. Okay. So what's the proper geometry for this type of plate? You know, a geometry that will help you solve this problem. We know from experience that the best geometry is that of a cylindrical geometry. And that's why I drew this cylindrical surface right in here. Don't forget, every time that we are solving for Gauss's law, we must come up with a closed surface. Okay, so we have this side surface number 3, the cylindrical side surface number 3. We have, and then you have this cap 1 and cap 2 here on the other side. I dashed this cylinder because I want to give you, I want to pass you the idea that this surface is an imaginary surface. An imaginary surface that's very useful to help us solve a problem. Okay. So don't forget there is another surface right in here. The surface, there's another cap here. Okay. So here you go. What else do we have to know? We have to know the area, the direction of the area vector. This surface, this cylindrical surface right in here, the area vector points perpendicular, normal to the surface. It would be something like that, which, by the way, ends up being perpendicular to our qualitative electric field. Okay, and then the area vector for the other caps is going to be what? It's going to be parallel to the electric fields. Okay, parallel here, and parallel here as well. Oops. Oh, should be not A3, should be A2. I call it A2. I'm labeling them with different numbers because they are different vectors. It's parallel here, it's parallel there, but it's perpendicular here. Okay, so we have 3 surfaces: surface number 1, surface number 2, and surface number 3. So what do? We go ahead and formulate Gauss's law. Here we go. Let me write it down. We can draw. Oh, let's see. Due to the symmetry of the problem, we can draw a cylindrical closed surface that encloses a small amount of charges of the plate. Okay, so here you go. This surface here is enclosing this charge here. See that's my enclosed charge. Okay, that's my enclosed charge. This charge here is not enclosed, this charge here is not enclosed. And by the way, the plate has uniform distributions of charges, by the way. Let's write it down. Find the electric field of a very large flat plate of uniform charge distribution. It's already in there. And net charge Q, net charge Q of net charge Q and area A. This cylindrical closed surface is made up of 3 open surfaces. The cylindrical surface per se, the cylindrical surface, let's see what I labeled here. Okay, 2 caps, let's put it this way. 2 caps, surfaces 1 and 2 in the slide, and the cylindrical surface itself, number 3. Okay, and now we go ahead, we apply the equation for the net flux, electric flux through that cylindrical surface. Okay, so it's going to be something like that. Here you go. Electric field, I'm going to write it down. Electric field 1 times surface area 1 cosine of phi. I'm going to put that cosine of phi 1, right? Electric field on surface 2 times area 2 times the angle 2. That's going to be the electric flux, and then electric field on region 3 times electric field on the surface 3, right? Electric field times the area on the surface of the surface 3 times the angle between the electric field and the area vector. Okay? Like I mentioned before, the electric field here is perpendicular to this area vector 3. Consequently, this term here disappears. I'm going to be very explicit about that. Here we go. This term here is going to be 0. For areas 1 and 2, the electric field is going to be parallel to these two area vectors, right? So here you go. So the angle phi is going to be 0. This cosine is going to be 1. Again, here also we have this situation. Cosine is going to be 1. What else? Because we're dealing with a cylinder, the area 1 is going to be equal to area 2. Okay? I can erase this guy. And let's not forget, you know, Q enclosed on the left side. I'm going to write down in terms of the K parameter that you're more familiar with, 4 pi K. Okay? Q enclosed. Now, what else? This Q enclosed, by the way, don't forget that is a uniform charge density. I told you that net charge is Q. And by the way, I should have, okay, I'm going to put A prime here, okay? I have to use A prime here because this, the area of the cylinder is different from the area of the plate. I'm using A for the area of the plate, okay? So here we go. Q, let's see here. You know, because Q over A is a parameter that we call, and that's going to be the, yeah, that's the A. Because the, you know, because the charge is uniformly distributed, we have the following relation, okay? The net charge divided by the net area of the plate is going to be equal to the charge enclosed divided by the area of those two of the caps of the cylinder. Make sense? Okay. So here you go. This area here is what I'm calling A prime, not A, right? A is the whole area of the surface. It's the whole area of the surface. Okay. And by the way, this thing here, this relation that you see here has a name. It's called, you know, charge density. In the above formula, sigma, okay, which is represented by the Greek S. What did I do here? Symbol, yeah. Symbol. Okay, is called the surface charge density. Okay. Also written, that can also be written in a different way, delta Q over delta A. like that. Charge density. Okay. And let's continue here. And look what happens to the surface charge density, you know, when we write Q enclosed in terms of the known parameters. Look what we get. We get something like that. A prime here upstairs. Now that we have a relation for Q enclosed. Okay, now that we have a relation for the Q enclosed, we can substitute. We know A and we know Q. What we do not know is A prime. What we do not know is A prime. But let's substitute this Q enclosed in this equation right here. I already wrote it down, right? So here we go. Okay, I'm going to substitute this one right here. Here you go. We know A and Q. I gave you A and Q, but we do not know A prime because it's a arbitrary surface, the one that I drew in there. It can be any size I want, but we still don't know it. What happens with this A prime? We cancel with the other two A primes here. Do you see that? Okay. So here we go. We have, I'm gonna put A priming evidence on the left side. Okay, like that. I cancel this A prime, cancel out with the other one. And now we have the field on the left summed with the field on the right. And there is one more trick that we can come up with. A trick that's not obvious. And by the way, you know, to simplify my notation, let me write down this guy here as being sigma. Okay. The surface charge density. Okay, now we are going to do a little nice trick here that books don't teach. Okay, what are you going to do? I'm going to make this distance from here to this cap equal to the distance from here to this cap, to the other cap. Okay, making the distance from the charged plane to the first and second caps equal to each other. Okay, if we make the distances of the caps 1 and 2, the distance of the caps 1 and 2 to the charged plate the same, okay, we can realize that both electric, that the electric fields on both sides of the charged plate will be equal to each other, or you know, or because let's say x1 equal to x2, right? Let's write that down. D1, distance of the cap 1 to the plate, comma, then we can state the distance of the cap 1 equal to the distance of the cap 2. Then we can state that E1 is equal to E2 because the sources are from the same distance. The charge. That's a very reasonable assumption, which, by the way, we are going to simplify this notation by stating that it's equal to E. Having said that, here you go. We are going to finish that now. We finally find that what is in the left side is going to be 2e. Okay. I will write that down in terms of that. And finally, we obtain that the electric field on both sides of the plate is going to be 2 pi k sigma, or, you know, there's another way to write that down too in terms of epsilon naught. In terms of epsilon naught, it's going to be like that, 2 epsilon naught. Okay. But that's just one plate. Okay. Is it what you got in the book? Let's see if it's exactly what you got in the book or not. Heck. Let's see here. Gauss's law. It changed my. I gotta go down there again. Gauss's law. Go. One more student coming in. I'm gonna take attendance soon. See, Gauss's law. Yeah, here you go. Oh, here you go. Okay, see, he did this problem here with the positive and negative charges. Plates, right? Planar plates. And he used the same Gaussian surface. I prefer to do the other way, right? But note what he got here. He got a result that's different from mine. It's twice mine, okay? And there is a reason for that. The reason that he got twice as much is because he's solving this problem here, whereas I'm solving only this problem, okay? That's the reason. How do I get the same result that the book got? Okay, so this value is explained here in my drawing, okay? So here you go. Let's see. Okay, here you go. This one's supposed to be negative. Okay, but we are interested in the next drawing. Here you go. And this one here, let me see. Okay, this one is supposed to be negative as well. Yeah. Okay. So note that for a positive plate, the fields are away from the positive plate, right? But for a negative plate, the fields must be towards the negative plate. This drawing too is supposed to be a negative. That's what we did for Lec Lab. An illustration of what we did for Lec Lab. Okay. Now we combine those two plates together and we use the superposition principle. Okay? The positive charges are going to have these blue fields that you see right here. And by the way, one important thing that I have to mention. Note C that this electric field does not depend on the distance, okay? Note C that this final electric field does not depend on the distance to the plate, to the single plate. Consequently, it depends only on the surface charge density, which is uniform. Okay. Consequently, the electric field is also uniform. Okay. Now, here you go. Let me break it down into two different slides now, so you do not get overwhelmed by too much stuff here. I'm going to remove only what's red from here. Okay, go 1, 2, and I already did that before, right, in the previous slides. But let's do that. Here we go. That's what the electric field of the positive plate should look like, and it's equal to sigma over 2 epsilon naught. And the field of the other plate, of the negative plate, is going to be also sigma over 2 epsilon naught. The only difference being that's going to be the direction of the field. Okay, and I'm going to erase this one right in here, right? Because you have a negative field, a negative charge, the field should point towards the negative charge. When you combine this drawing with the other drawing, oh, this one's not supposed to be here. This drawing with the other drawing, you get this drawing here. Okay. Yeah, I erased that. Let me see. You got the idea, right? Let me see if I copy this one here. I'm just going to, here you go. I'll get this one here. Copy all of that and then paste it. And now you got it, okay? So here you go. We see the volume of those two plates. You have an electric field that is superimposed with the other one. You have twice the electric field here inside. Is sigma over 2 epsilon naught plus sigma over 2 epsilon naught. On the outside, the fields point in opposite direction, whether it's here or there, okay? And the net result is something like that. Fields equal to 0 on the outside and fields twice as much on the inside of each of those plates, okay? So that's what you had at sigma over 2 epsilon naught becomes sigma over epsilon naught. And let's not forget, this is a negative here as well. 240, we have one. So those are the examples. That there are more examples that we could do, okay, but I'm going to stop here for the Gauss's law. We could also have done examples of the uniformly charged sphere, okay? Start thinking about that, how it would look like. A uniformly charged sphere is this geometry right in here. Not the shell, but the uniformly charged from the center to the outside. Okay, it's we could also have done a problem like that, a linear charge distribution. We can do that as well using Gauss's law. Okay, I want you to think about that, how to do this type of problem as well. And the uniformly charged cylinder. I'm going to stop here and move forward. Any questions? Let's see. I don't see. Let me take attendance. And then we have our break. Today is the 20th. Huh? What's going on here? Huh, strange. Let's see if I can get that. Nah, it's not. It's misbehaving with me. They're doing another way. Here you go. Now you got it. Randy, are you there? I'm taking attendance right now. I didn't hear you. Are you there, Randy?
Yeah, I'm here.
Okay, good. Thank you. Vanessa Bonilla. Okay, thank you, Vanessa. And Ashley Diaz.
I'm here.
Okay, thank you. And Natalie Espinosa.
I'm here.
Thank you. Janet Garcia. Janet, right? Nice. Can you, I cannot hear you, Janet. Okay, good. Thank you. Next is Noor Hassan.
Here.
Thank you, Noor. Blanca Hernandez.
Here.
Thank you. Kaylee Hernandez.
Here.
Thank you. Joshua Jimenez.
I'm here.
Thank you, Joshua. Alondra Lima Abarca.
Present.
Yeah, present.
Yeah.
Okay, thank you. I see you here. Kennedy Lindsay.
Here.
Thank you, Kennedy. Daisy Mariscal.
Here, Professor.
Okay. You came very low. Daisy. Okay, I see you. Thanks.
Oh no, I was
Yes,
here. It's just my laptop died, so I reconnected.
Who are you referring to?
Daisy.
Ah, Daisy. Okay. And Yesenia. Are you there, Yesenia? Yesenia Montes Rodriguez. I don't see Yesenia here. Okay. Ryan Ong.
I'm here.
Thank you, Ryan. Artur Pacheco. Okay. Thank you, Artur. Lady Lut.
I'm here.
Okay, thank you. Donia.
Here.
Thank you, Donia. Elika Vate. I don't see Elika here. Okay, so, and Brianna Valencia. Okay, Brianna is here. Justena Youssef. I don't see Justena. Now let's see. Let's see here. Oh, it's supposed to be the 22nd. Sorry, folks. So here you go. Some here's the 22nd. Okay, this one is supposed to be on the other one. That's, I have a total of 17. Yeah. So it's 2:46 right now. Any questions before we proceed for a break? So here you go. Break. We're gonna have a break from 2:47 until let's see, 50. No, it's not 2:47. Sorry. Let me change here my. Is 9:47. 50 to 10:02. Yeah, 10:02. Okay. So I'm going to pause the recording, and when we return, please remind. I am back here, and what I want you to do is, I want you, at the beginning, I asked you to upload your spreadsheets, right? Just the spreadsheet, no need to upload it. Let's concentrate on the spreadsheet alone, just to make sure that you're doing everything the way I like to do, or in the way that should be done, right? Not just the way I like to do, but in the way that should be done. Chico. Break. Things that we can have. 17 lab. We have 18. It looks like we have one more student that showed up. Who is that? Let's see here. Elika, are you there? Let me go through my. Yesenia, are you there? Yesenia is not here. Elika, are you there? I don't see Elika. And Justena. Nope, I don't see Justena. Okay, so 18. Okay, now we have 17. That's good. So please don't forget. Please don't forget to upload your spreadsheet to your group folder. Right, and let me see. Let me check here. Google Drive. I want to stop sharing. Let's see. 2023 Physics 7 group folders. Okay, group 1. Okay, so Artur Pacheco, right? Group 1. Yeah, Artur Pacheco. Don't forget to label your spreadsheet in the same way I did here. P07, L01. That's the first thing that I ask from my students. So please correct. You can delete, right, this document here. Let's see. Yeah, that's right. You can delete that and rename it exactly the same name that you have this one named. Okay, let's start with this one. Okay, the group number 1. Okay, please rename it as P07L01G1. That goes for everybody else. Okay. Group 2. Let's see. Yeah, here you go. But let me see. Let me see this one here. Doesn't look like. Group 2. Did you upload your spreadsheet, group 2? Let me see here. Let me. Okay, so Ashley Diaz, Natalie Espinosa, and Jeanette, did you upload your spreadsheets? I don't hear from any of you. So here you go. 3, right? Upload spreadsheet. Okay, group number 1 did, right? Group number 2 still didn't do it. So let's go to group number 3. Group number 3. Okay, so it looks like, let's see if they did it. Okay, looks like group number 3 did it. Let me download it, and I'm going to comment very quickly.
While you're commenting, can I ask you a question?
Yeah.
Okay.
Yeah, you want to ask a question?
I'll wait for you to pull up the spreadsheet first because it has to do with the spreadsheet.
Okay, let me download it first.
All right.
Let me go through every group, okay, and then I want to make sure everybody uploads their spreadsheet first, and then I
Okay.
get back to you. Okay.
Thank you.
Okay, group number 4. Let's see. Group number 4, did they do it? Looks like they did, right? Okay, so let me upload that as well. Group number 5. Let's see. Yeah, group number 5 also did, right? So download it. Group number 6. Let's see, group number 6 did upload. Yeah, looks like group number 6 uploaded. Downloaded. Group number 7. Okay, so group number 7 apparently uploaded it. Okay, so download. Good. Now, let's see group number 1. Did you correct that group number 1? Yes, you did, right? Which one? 21st. Let's see, is this one here? Yeah, that's the one. Okay, let me download that. And this one here. Yeah, this one you don't need that anymore. Group number 2. Let's see, group number 2 doesn't look like group number 2 uploaded. So group number 2, are you there? Let me go back to group number 2. Ashley, are you there, Ashley?
Yes, I'm here.
Okay, were you able to do the spreadsheet for lab number 1?
Yeah, I have it with me. Let me just upload mine because I think I have it over in my Excel.
Okay, please. And Natalie, what about Natalie? Are you there?
Yeah, I'm here.
Okay, good. So same thing, right? Were you able to work on your spreadsheet the last time?
Yeah, I'll try to add on to it too.
Yeah, work with Ashley and Jeanette, okay?
Yeah.
So just to upload just a single spreadsheet.
Okay.
Okay, thank you. Everybody else here, yes. Okay, here's all right. Yesenia, I don't see Yesenia. Someone asked me a question. Let me see. Okay. Or email. Okay, so let's start. Let's start with group number 1. Here you go. Group number 1. Okay. So here you go. Okay, here is straightforward, right? X and Y is straightforward, right? All you have to do is to leave 3 decimal places because you are using a ruler that has a resolution of 1 millimeter. Okay, so that sounds good. That looks good. Here, let me see, group number 1. I don't see those numbers in the proper significant digits, okay? Maybe this one is. Let me see if this one is or not. I gotta get my. That's for group number 1. Let's see here. Group number. No, it's not this one. Group number 3. Group number 4. 5. No, 6. That's what I want here. You have to use that significant figure file, right? Let's see this one too. And I'm going to download this one as well. Okay, and okay, good. Significant digits. So I'm gonna put this aside and let's make sure. Now we have the units here, right? We need the units here. Okay, you're gonna put the units here, group 1. This one you gotta remember, right? This what you're plotting here is not okay. This table here is not the table for this graph. this table here is the table for this graph, right? And the table for this graph has only 5 data points, not 6. Okay. So that's make sure you fix that, please. Oh, the other thing regarding the CL, right? That's a constant. That's a mistake that I saw all the time, right? That there are 2 mistakes here. There are 2 mistakes here in the CL. Okay, so you type 10 to the 6th power. You didn't put 10 to the minus 6th power. Okay, so and there is this other one that should be 10 to the minus. That's assuming that the confidence level is okay. So there are 3 mistakes. I'll say 4 mistakes, right? The negative sign here, that mistake 1, that mistake 2, and then there are 2 more mistakes. 2 more mistakes. When you type that, anybody else, okay, anybody, when you type that in Excel, Excel thinks that what you wrote here is a text, not a number. Excel treats that as a text. In order to make Excel treat it as a number, what you have to do, you have to put an equal sign right in here, okay? And an equal sign right in here. Make sense? Everybody, okay? So Excel can do the math for you. Make sure you do that. Don't type it. Don't put that as a text. Otherwise, you're gonna miss the points here. Okay. So I'm gonna undo what I did. I'm gonna return to the old one. Okay. So here you go. Significant figures here. Significant figures here. You don't need significant figures here. Okay. So you gotta look how. You got to study carefully how many significant figures you're supposed to have. Okay, in this case here, you're gonna, in this column here, you're gonna have two significant figures, right? Here you're gonna have 2 as well. Here have 2. Here you have 2, and here you have 3. Okay. And what's gonna happen? You're gonna take the average of each of those columns. Okay. Before taking the average, you have to sum, right? You have to take the summation, make the summation. Here you go. Only for X, right? And you do that for the other ones as well. You go X, 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 and X. Okay. And then for the case of the summation, what do? You preserve up to the 3rd decimal place, right? You preserve the significant digits up to the 3rd decimal place. So what I have here is correct. And also note something else. You have 2 significant figures here, 2, 2, 2, 2, and 2. But here, when you sum all those values, all those measurements, you end up with 3 significant figures. Okay, that's that's exactly what we do in research. When you perform a measurement several times, you end up increasing the number of significant figures of your result, and that's what's happening to the X position here at the equipotential of 2 volts. If you end up having 2 significant figures here, 2, 2, 2, by summing, you end up having 3. And then you take the average, divide by 6, right? That's what I did here. Took the average of those 6 measurements. You are supposed to display 3 significant digits here as well. Okay? And you perform the same thing here. Let's see if this value is correct. Okay, number of significant figures for the voltage. I'm looking here at this document that I gave to you. We were using a specific multimeter that was displaying a proper number of significant figures there. And when you do the experiment, you have to look at that. Let's see what's going on here. Okay, voltage DMM. That's the table that you have to look at. Okay, you have the first table, resistance DMM. You don't want that. You have this other table here, power supply. You don't want that. You want the voltage VMM because you use digital multimeter to measure the voltage. Now, we've seen ranges between 2 volts and 9.99. Okay, how many secant digits you're supposed to have? You are supposed to have 4 secant digits. Did you put 4 secant digits there? Yeah, you did. 4 here, 4 here, 4 here, 4 here, 4 here, 4 here. 0 to the right of a secant digit is considered a significant digit. That's good. Now you gotta work out the rest for 6, 4, 8, right? 9. And also this table, right? You don't have to worry about secant digits here, but you have to worry about the units here. And the last one, don't forget this one too, the charts are important. Okay, you labeled the axis, that's good. And you didn't label the axis in this one. Here goes V average and X average, right? And you have to fill this table. You have to fill this table, both for the units and the values. Okay, group number 1. So let's go for group number 2 right now. Let's see if I have number 2. Group number, I'm gonna close it. I'm not gonna save it. Group number, let's see if number 2 uploaded their spreadsheet. Let's see. Yeah, I don't see any work here, right? Yeah, I don't see any work here. Let's go for group number 3. Group number 3.
Hi, this is Ashley from group 3.
Yeah.
Right now, I'm just trying to share the document with them so that we can do more work on it.
Oh, okay, okay. You're group number 2, right, Ashley?
3.
Ashley is number 3.
No, you're group 2.
You're group 2. Group 3, someone else. Someone else. See, that's group.
Oh my God.
Yeah, group number 2.
It's all
Ashley, Espinosa, and Garcia. Yeah, that's group number 3. Okay. So make sure you have the correct link, right, for your group folder. Do you have the correct link for your group folder, Ashley?
Yes, I do.
Okay, good. Okay, so let's go for group number 3 now. So group number 3 had a question, right, Kennedy? You had a question?
Yeah, but we could go over it once you're done, just because it's
Okay.
about the input of the very last table.
Okay. Okay, so let's see. This seems to be good. Yeah, don't forget to put the units here, okay?
Okay,
Don't forget. All you have to do is to copy and paste here. All
right.
the units are the same. Okay, and you gotta put the units here as well. Units here, and here, let's see. Yeah, it's 5, that's good. Here you put the straight line, right? Yeah, you don't plot with the lines connected, okay? Plot with the lines not being connected. Let's see here.
Okay.
This one, that's easy to fix, right? So conditional formatting, where's that? Insert, that's what I
Yeah,
want.
for table 1.3, I don't know if I need to keep the minus 0.0995 in,
Okay. Mhm.
but I
Yeah,
couldn't get it to align.
Yeah, okay, so what happened here? What this G361 is all about? Yeah, see, you put this G361 here. Looks like by mistake, right?
Yeah.
Okay, it's not G, right? It's gonna be 1, right? And 1. Okay. And now hopefully that's the right CL. Okay.
Okay.
So what you had before was, I do not know why, maybe you accidentally clicked that cell.
Yeah, I was
Okay.
clicking around because I was trying to get the the table to look a little better.
Yeah. So now you put the number 1 here, right? If what do you want to do? You want to right justify? You want to left justify? What do you want to do
No,
here?
for the regular equation for the voltage average.
Voltage okay, voltage average.
Right above, no, go down in the 1.3,
Oh, yeah,
right above
okay,
our screen.
okay, I got it.
Yeah.
Yeah. I see, that's the equation. Okay, good,
Yeah.
it looks good. If you want to make it look better, just, stretch a little bit more the cell, right? Let me,
And should they all be bold?
no, it's a mistake here, okay? The only thing that's bold is writing here,
Gotcha.
okay? We don't usually make the data bold. Okay, now the problem is you're asking this table here.
Yes.
Okay, so the slope is just what you see here, right? 55.598.
Okay.
And for the uniform field, the slope itself is the field. So if you have
Oh, okay.
55.598, you write down 55.598 too. Okay.
I see.
Okay, well, but wait a minute. Here's the units. You gotta write the values here. You gotta
Okay.
write 55 goes here, 55 goes here. And then don't forget the units.
Gotcha.
Let's
And then,
see if I'm-
sorry, for the second table,
Uh-huh.
you just, because I forgot to label it. So we need X average, and then you said,
Yeah, you need the units here, right?
no, I mean, I'm sorry, for the second graph, I meant,
The second graph. Okay.
apologies.
Yeah, you need to write down the labels, right? The average, parenthesis unit, X average, parenthesis unit.
Okay.
Okay. You know
Thank
how
you,
to do
sir.
that?
Yes.
Okay, good. And what else? Let's see if those numbers are correct. Okay, so those are correct because it goes to the third decimal. Okay, third decimal, right? And third decimal. Okay, good. And what about the voltage? Voltage between 2 and 9 is 4. Okay. And 2 and 9, okay. Yeah, all the way down to 2 and 9 is supposed to be 4. You have 4 here, we have 4 here, we have 4 here. Let's see. Above 9, what's the number of sequence digits? Let's see. Oh, it's 2. Okay, it's 9.99. So everyone should be for this sequence digits, okay?
Yes.
Everyone here should be 4. Okay, so you're in good shape here. And okay, you plotted. Okay, the only thing that's missing, right, is the equipotential curves. You gotta draw a line through, and also the electric field lines.
Okay.
That should be uniform. That's group number 3. Now,
And then,
what?
are significant figures for the second table good?
Oh yeah, that's right. Second table is a little bit more difficult, right? So
Yeah.
here you go. Let's do the sum here. Sum. Do we increase the number of second digit? Yeah, you do increase the number. From 2, you end up with 3, right? So this
Okay.
one is going to be 3 second digits. What about this other one? 3 second digits as well. This one. Okay, we will stay 3 second digits. Will remain 3 second digits. Okay.
Okay.
And what about the next one? Yeah, this one is still 3 as well, because the summation has 3. What about this last one? Yeah, 3 as well. So you gotta fix those 2. Okay.
Okay.
And you gotta do the same for the voltage, right? Here you go.
Yeah.
Here you increased from 4 to 5. Here too, you should increase from 4 to 5. What about here? You increase from 4 to 5. From 4 to 5, and this one, yeah, it's still from 4 to 5. Everybody's going to be from 4 to 5. 5. You have only 4 here.
Okay.
Okay. And I do not know if those CLs are correct, but I presume it is. Okay.
Right.
now let's see. I'm
All
going
right, thank you, sir.
Welcome. I'm gonna close. Don't save it. Let's go for the next one. Group 3, group number 4, right? 4. Let me put group 1 here. Ah, didn't help. Okay, so group number 4, we want group 4 right here. Okay, so 4, 4, yeah, we already know it's 4, right? All the way down to, all the way up to 9.99 is going to be 4 second digits. Good. Here's 3 decimal places, 3 decimal places, 3 decimal places, right? 3 decimal places. That's good. We have, okay, all the units here. Okay, okay. And now this one here is meter divided by meter. Okay, group number 4. Are you there, group number 4?
Yeah, we're here.
Okay, good. Well, meter divided by meter, you gotta do the math, right? The algebra. You display as 1. Okay, the unitless unit. Okay. And here it's the same thing that we did before, right? Get the summation for everybody, and then you analyze to see, to find out what's the number of significant digits. The only one that you cannot do is the one for y. For y, you don't do it. Because y doesn't repeat, right? The y keep on increasing, keep on changing, right? But here you're supposed to get almost the same value. Here you're supposed to get almost the same value. Okay, and now you have 4 significant digits. When you sum, become 5. Divided by 6 is still 5. So you display 5 significant digits here. Everyone here is going to be 5. Everyone here is going to be 3. Here you have 2. Here you have 2. Okay, so you got to put 3 here and 3 here. You gain an additional decimal place, but you do not gain an additional decimal place here. Okay, yeah, see what they did? Here you go, good. They drew the equipotentials, right? And then drew the electric fields, 1, 2, and 3. 1, 2, and 3. We have the nice edge effects here. White and between parentheses. That's good. Okay, that's good. X average. And then we have, okay, units. Okay. Here. Okay, 5. That's good. So I don't see anything else there. Okay, so group number 4. I don't want to save. Let's go group number 5. That's group number 5. Okay. Oh, yeah. Okay. You put additional decimal places here, right? Group number 5. So Vanessa Bonilla, Blanca Hernandez, and Joshua, right? So you gotta take out the decimal places here.
It's we have been having issues because we did it in Excel, but for some reason when we uploaded it to the Google Drive folder, it just messed up all the values because on my Excel folder right now, I have the actual right units, but I don't know why when we switched it, it just so I'm trying to fix it up right now to get it work.
Yeah, I never heard of Google Drive doing that. Okay, but let's do a test here. I'm going to put the right number of significant digits here. I'm going to upload, okay? Format cells. Number. We want 3 decimal places for everyone. We have everything with the right number of significant digits now. 1, 2, 3, 1, 2, 3, right? I'm going to, let's see, save this one. I'm going to upload. Okay, did save it. Group 2, group number 5.
Professor, should we name
Yeah.
all our graphs?
Name.
Yeah, like
don't
the
have to.
like this group has equipotential curve as the title of the graph. Should
You mean like they did here?
yes.
You don't have to. I don't. Yeah, I don't. I myself, when I write my papers, when I plot my graphs, I don't put the title in the graph. Okay, but
Okay.
whether you put it or not, it's going to be indifferent for me. Okay, I'm not going to take out points because of that.
Okay, just making sure.
Okay?
Thank you.
That's just a personal. So let's see here. Group number 5. Okay, I'm uploading it. Okay, this is the one that I uploaded. Now I'm going to download it again. Let's see if it changes, right? Let me see. I see. Okay, I see the format, the proper format. Let's see. I never, like I said, I never had this problem of Google Drive changing the. I'm going to delete that, remove. Now, let's see if it changes anything. Yeah, it didn't change, right? At least in my case, it didn't change. So you can do you can fix there on your side, and then later on I will upload again to see if it changes or not.
All right.
Yeah. Who's that?
It was me, Josh. I said okay.
It's okay? Okay. And second digits here, right? Summation. You go. That's why we do not want y. Good. So you go. So just like before, right? Here you go. You increase from 2 to 1, increase from 2 to 1, remains the same. Oh, this one increases. See that? From 3 to 4. Okay. This one also increases from 3 to 4. So you gotta adjust it here. Let's see. X average. Yeah, 3. You have 3 here. You have 3 here. You have 4. Right? Supposed to be 3. It doesn't go above, when you sum, it doesn't go above 10. But this one goes above 10. So you're supposed to have 4. You have 4. You have 4. That's good. Okay. What about this one? Yeah, 5. Yeah, 5. 5. 5. 5. 5. 5 and 5. Okay, that's good. Units. Well, okay, you have the axis. Okay, this one you mislabeled. Okay, you mislabeled those I'm correcting. So make sure you put the average here with the right unit, and you put x average here with the right unit as well. Okay. Okay, here's a problem. Okay, definitely there's a mistake here. Okay, the slope is 42.189. That's the slope. Okay. And the field is also 42.189. The field strengths. Okay, so you gotta fix that. Let's see, how do you get? I believe you took the inverse, right? Yeah, you took no, you didn't take the inverse. How did you get this 0.27? Ah, you got the intercept. Okay. Instead of writing the slope, you wrote the intercept. Okay. Group number 5. So make sure you fix it, that, please. Okay, group number 5. Don't save it. What about group number 6? Are you there, group number 6? 10:39. Hello, group number 6.
Yeah, I'm here. We're here.
Okay, thank you. Who is that? Is that Lim? Is that Alondra, Daisy, or Yesenia? Yesenia didn't come
I'm
to-
the one who spoke, Alondra.
Alondra, okay. So let's see. Okay, so you already know that. Okay, so you put too many second digits here, right? In this one. In this one, just go back to that document. Here you go. Between between 2 and 9, right? You are supposed to have 5 or 4. Yeah, 4. You're supposed to have 4. Here you have 4, but here you have 5. Here you have 5. Here you have 5. Gotta fix that. Okay, Alondra? And everything else goes to the third decimal place. Third decimal place. Third decimal place. Okay, this one is not third decimal place. You went to the fourth decimal place. Okay, and this is supposed to be third decimal place as well. So okay, so this one is good. The only one that needs to be fixed is this one. And okay, this one needs to be fixed as well. Oh, this one, right? Yeah, and this one's here. And here is my equipotential curves. Make sure you draw a line here showing the equipotential curve and also the electric field lines going from the right to the left. From the right to the left. Okay. Okay, X average again. Here you go. Just like we did with the others, right? First, you get the summation, and you figure out how many decimal places the summation has. How many decimal places now? How many second digits the summation has? For the 2 volts should be 5. For the 4 volts, 5, 5, 5, and 5. So it should be okay. They have 5 here, 5 here. The only incorrect one is this one. And what about this one here? It should be 3. Okay, x3, 3, 3, 3, and 4. The last one is 4. 3, 3, 3, 3, and 4. Okay. Someone else is coming. Let's see. Jeanette. Okay, and good. The average, X average, that's good. Okay, yeah. Strictly speaking, you know, you're supposed to put the E field negative here, right? Strictly speaking. Because the E field is minus delta V delta X. Minus the slope. The E field is minus the slope. This one seems fine.
Professor, I have a question.
Yeah.
For group 2, we're trying to upload our lab, and every time we do it, for some reason, our graph completely changes into if we were using like Google Sheets.
Let's see.
So it isn't showing like the proper Excel graphs.
That's normal. That's normal. But you use Excel in your computer, right?
Yeah.
Or you use Google Sheets. Okay, let's see. Let me download it. That's the one 1022. Yes, that's normal. Okay, when you open in Google Sheets, it doesn't display everything the way it's supposed to display. But when you download it, you do see it properly. Okay. Okay. See, you don't have the. Did you do the second digits? You do the formatting. Okay, group 2. And we go. Let me see. Yeah. So make sure you work on the formatting of the data, group 2. Okay, I see the graphs here. I'm gonna put the axis title, and there's a missing graph, right? Yeah, you need the second graph, this graph here as well. Okay, and you also have to work on the units. I don't see the CL. Okay, does your original document has all that stuff or not, Ashley?
Yes, let me just get it uploaded.
Okay, so I'll get back to you. Let me go to the student I was talking to, right? The group, which group I was talking to? Group number 6, right? Yeah, group number 6. Group number 6. Yeah, okay. So group number 6 gotta take a look at this table, right? And maybe let's take a look at the CL, if it's right or not. You go. It's 5 data points. R square is 0.9982. 9982. Okay, 9982 is between those two values. Consequently, it's 1 minus 10 to minus 4, 1 minus 10 to minus 5. Let's see. 1 minus 10 to minus 4. Yeah, good. Good. So the CL seems to be right. Okay. So it's 10:46 now.
Professor.
Yes.
So we got a few of the sig fig, or we got them a little bit like wrong by how many we're supposed to have, right?
Which group are you?
6, Alondra.
Yeah, Alondra. Okay, so here you go. X average is supposed to be 3. You put only 2 here.
3, 6. Oh, 2. Okay.
Here's
Okay, I see.
3. You put only 2, right? 3. You
Okay.
put only 2, 3, 2, and the last one is supposed to be 4. You put
Okay,
only
I got it.
okay.
Okay.
Just look at the summation, right? And
Okay.
here, right? Here you put 4. It's supposed to be 5. 5, 5, 5, 5. Everything should be 5. The only, yeah. Okay. And the unit, right? The unit is not meter. It's meter divided by
Okay.
meter, which is 1. It's
Okay.
let's go in a break now. And 7:48 right now. And there is one more group that I have, I'm going to display here. And don't go yet, because since we are, we may have a little bit more of time, I want to cover a little bit more of the material, okay? So here you go, PO7 notes, break. 10:50 to 11:05, right? So I see you in 15 minutes. And I'm back here. Okay, the only group that we have left here is 7, right? Let's get the. Okay, so let's see. Okay, we already know it's 4 digits, 4 significant digits. So we have 4, 4, 4, 4, and 4. 3 decimal places, 3 decimal places, 3 decimal places, right? 3 and 3. Okay, and then you gotta do the significant digit here because we're gonna take the average of those values. Okay.
Professor, we can't see your screen.
Oh, yeah, that's right. Thank you for letting me know. Share. Let's see what's going on here. Share. Here you go. Now you see it. Hey, here you go. Okay, so here you go. 4, right? 4, 4, 4 in 4. 3 decimal places, 3 decimal places, 3 decimal places, 3 and 3. And now we have to find out what's going to be the significant digits of those average quantities. We find out the significant digits of the average quantity by being reminded that the average quantities is the sum of the quantities that we have divided by 6, right? We're not doing the average of the y's, we're doing just the averages of the x and the v. Good, so 5, okay, so here you go. 5, 5, 5, 5, and 5. So here you have to fix that, right? You have 4, 4, 4, 4. Okay, the unit again. This unit here is incorrect, right? If the unit for sigma is meter and the unit for x average is meter, then the unit for this quantity here is going to be meter divided by meter, which is supposed to be 1, a unitless unit. Okay, make sure you fix that. This average is going to be 3, 3, 3, 3, and 3. Everything is going to be 3. So you must have 3 here and 3 here. Here you have 3, but not here. Here everything should be 5. Okay. Don't forget to trace the equipotential lines, right? And the electric field lines. That's what's missing here. Good. Here we have 58, 58. Yeah, good. And let's see if it's 10 to minus 6 and 10 to minus 7. Let's see. Confidence level. R square. Yeah, 9999. Okay, number 5. 999. Okay, 9999. Yeah. Okay, so it should be at 10 to minus 6 and 10 to minus 7. That's right. 10 to minus 6 and 10 to minus 7. 1 minus 10 to minus 6 and 1 minus 10 to minus 7. That's average. That's good. Okay, and what about group number 2? Do you need help? Group number 2? Let's see if group number 2 come up with a. Did you update your spreadsheet there, group number 2? Let's see.
We're updating it right now.
Okay. Okay, so any questions? So that's what we are going to do the rest of the semester, okay? And units, most important of all is the graphs. That's the most important of all. Graphs, units, significant digits, CL, you know, and percentage difference. We didn't have percentage difference in this case, but we are going to have percentage difference in the other labs. So 11:20, 11:10 right now. Let's take, I want to take this opportunity to do chapter on the electric potential, okay? And then we can stay here until 12 noon, another 50 minutes to go. This is the one here on, we covered, let me write down the chapters we have, the sections we have done so far. So far, we covered the following material. 18.1, origin of electricity. 18.2, charged object and electric force. We did cover conductors and insulators, right? Let's see. Conductors, let's see. Yeah, we did, okay? So you have to know about conductors and insulators. And that's what 18.3 is all about. You can read 18.4, but I'm not going to. It's important that read, but it's not going to show up in the exam. Okay. Coulomb's law, yeah, we covered. Read, but it won't. That's how we charge. They're describing how we charge materials. You read, but it won't show up in the exam. But it will not show up in the exam. What else? Coulomb's law. Electric field lines. Okay. That's 18.7, 18.8. No, we're not going to do that. If we need later on, we'll do that. Oh, we did 18.9. Electric field lines. Let's see. Let's field inside a conductor. Yeah, that's not going to show up in the exam unless we really need. We covered that, okay? And I started also electric potential and potential energy. Here's electric field, electric forces and fields. Okay. And we started electric potential energy and electric potential. Electric potential energy and electric potential. Okay. Let me check the other notes here. Electric potential energy is important, electric potential, okay? Electric potential is important because it's the easiest quantity to measure out there. It's not easy to measure an electric field. It's not easy to measure electric potential energy, but it's easy to measure the electric potential with that very simple device that I showed to you last time, right? Multimeter, the multimeter or the voltmeter. Here you go. I have one that's fit in the palm of my hand, right in here. It cost me like $50. I use this thing here to ensure that my batteries are charged, and if they're not charged, I just throw them away, right? So if you ever struggle with electrical devices, electrical and electronic devices, it's always good to have one of those around to help you troubleshoot your electrical device to make sure that you're not using a battery that has been exhausted, that no longer has any energy. Okay, and how do you define electric potential energy? Okay, how do you define the electric potential energy? Okay. Well, we define exactly in the same way. We define exactly in the same way that we define the gravitational potential energy. In physics 6. Okay. Before we do that, we have to define something else called work. Okay. Before defining electric potential energy, there's a story right behind that. First, we have to define that quantity that we covered in physics 6, called, to define a quantity. The quantity we defined in physics 6 called work. Work of a given force. Okay. Work of a given force. And in this case, the work of the force that we have to define is the work of the electric force. I'm gonna do just like that, okay? Work of the electric force. I have to put a uppercase E here to denote electric force. In our case, the work of any force, right? Let's start with the work of any force. The work of any of a given force. Let's see. Before defining electric potential, comma, first we have to define the quantity. A quantity we covered, right, in physics 6, called work of a given force. Okay. The work of a uniform force is defined as, okay, what's that? F times delta x cosine of the angle between the force and the displacement. Remember that? Okay. But don't forget, this is the definition of the work of a uniform force. And I'm going to, if the force is not uniform, it's a little bit, this work is a little bit more difficult to calculate because it involves integrals, okay? If the force is not uniform, then this definition does not hold, because you need to do some integration, and this course is not integral based, it's not calculus based, so I'm going to leave aside. So, but for a uniform electric field, okay, a charge, right? A charge subjected to a uniform electric field experiences a uniform constant, a uniform force, okay? So now what we have here, you can extend this idea of the electric force. So the work of an electric force is going to be the force itself, the electric force itself, times the displacement of the electric charge, times the cosine of the angle between the force and the displacement. Okay. So let me illustrate that in terms of a uniform electric field. I have one illustration here. Okay, here you go. That's a good example here. Here you go. So you have not this one. Yeah, here you go. We have this one right here, and I'm going to go even further. I'm going to put this charge here at the top. Okay. So here we have this electric field, and this electric field is exerting a force on this electric charge. Because the force is along this direction, we are going to have a displacement that's going to be along this axis, okay, like that. So how do we calculate the work done by the electric force? The work done by the electric force is going to be the electric force times the displacement from here to here, okay? In this specific case, the force points in the same direction as the displacement. Okay? Points in the same direction as the displacement. Okay, so here you go. Can go down, right? Here you go. Here's the electric force doing some work on this electric charge, moving it from one place to another. The electric potential energy, no, that's the work done by the electric force. Now, the electric potential energy, is going to be minus the work done, just like we had just like we did before in physics 6, okay? So but before you go into that, for a uniform field pointing on uniform electric force pointing in the same direction as the displacement, right? Like the one-dimensional case that you saw, like the 1D case in the illustration. We have that the thing reduces to something like that. But since we have a uniform field, the work done in my charge is going to be QE, and the force disappears, right? That's what the force is. That's what the electric force in a uniform field is. Now, the electric potential energy is going to be what? It's going to be minus this thing here that you see here, just like we did in physics 6. Or, electric potential energy is going. Electric potential energy. Let's see. Actually, it's the electric potential energy difference. Okay, electric potential energy difference, and I'm going to denote that as delta. Let's see how I'm going to do that. Delta. Yeah, we usually denote electric potential energy as U. Usually do that, which is, by the way, the final potential energy minus the initial potential energy. is going to be minus the work done by the electric force. Okay, which is going to be, don't forget, we're doing that for the uniform electric field, where this delta X is going to be X final minus X initial. Okay. That's what we have. And now compare that to the gravitational potential energy that we saw in physics 6. You know, the gravitational, and I'm gonna, again, I'm gonna put like that so you can, and I'm also going to put E here so you know is the electric potential energy initial and final. Let's go this way. Compare that to the case, the gravitational case. I want to put the lowercase g, g, g. Okay, and that's going to be gravitational force, g, oops. And then what's going to be here? Is going to be m without the minus, right? Let's see, potential energy, m g, not delta x, but delta y, right? Y final, y initial. Here you go. The difference in sign, that's because the g is downwards and y is upwards. That's the only difference here. Do you see the parallel between electric potential energy and the gravitational potential? Okay. Compare that to the gravitational potential energy nearby the surface of the Earth that we saw in physics 6. So that's the first electric potential energy that you have to know. The one for a uniform electric field. Okay. And what about the electric potential? What is the electric potential? What is the electric potential? Okay, the electric potential is nothing but, and we denote that by delta V, okay? Electrical potential difference. We call that electrical potential difference. Is going to be delta V, V final minus V initial. Now I don't need the lowercase e, because that refers only to electrical quantities. Now the lowercase e becomes redundant. And let's drop that. When we did that for the U, it was important to keep the subscript here to differentiate the U due to electric forces and the U due to gravitational forces, okay? Now, the electric potential difference, how is it defined? Is nothing but the electric potential energy difference divided by the charge itself, okay? Which ends up being what? Without the Q. Something like that. Okay. which was exactly the same thing that you saw in the lab. Remember, I told you that the electric field is minus delta V over delta X, right? Which is the slope minus the slope that you got that in that result in that lab. Okay. And the analogy with gravitational force is pretty straightforward, right? Here you go. Compare this situation here of the positive electric charge with the mass in the Earth's gravitational field, right? It's completely analogous to what we saw there in physics 6. Let me, I think I have a better drawing here for that. Yeah, right here. Here's the case of the mass, right? Of the Earth's mass. The mass next to the Earth's mass, right? This mass tends to go toward the center of the Earth. Now, if you have a charge that's negative and another test charge that's positive, this test charge also tends to go towards the center of the larger charge. If we raise this mass against the gravitational field, we are pumping potential energy. We are adding potential energy. Similarly, if I have a big charge, negative charge, attracting a smaller positive charge here, if I separate both of them, I pump electrical potential energy into the system. Okay? So that's for a positive and negative charge. Okay. Now, for when the two charges have the same sign, you know, the situation is different, right? The situation is different. So you must do work to make the charge. You store potential energy when you approach the two charges. Okay. You increase potential energy when this charge is closer and closer. And naturally, those charges tend to separate. That's an important difference between the electric force and the gravitational force. Electric force can be attractive and repulsive, but gravitational force can be only attractive. 11:34. Any questions? Okay. So that's electric potential difference. Okay, so we cover electric potential energy difference. We covered electric potential energy difference, and we also covered electric potential difference. Electric potential difference. Okay. Now, what about the electric potential? How do we define electric potential? Electric potential is defined as the electric potential energy. My notation is different from the book. Okay, here you go. Defined as, you know, V electric potential divided by the charge. So it's the same definition for the difference. Okay. Okay, so let's do an example. Okay. So you can understand better this idea. Example. Interactive field 19.2. I'm going to do my own example. Here you go. Example 1, right? So now that we have come up with those ideas of electric potential energy, now we can use conservation of energy to find some important parameters of our charge. Okay. So by the same by the same token, we have a potential energy, an electric potential energy. We also have conservation of energy for a given electric charge. Okay, so we are going to do just that. We're going to do an example. Going back here. Right here. Okay. Consider, consider this situation. Example, consider a positive electric charge next to the positively charged. Let's see. Consider a positive electric charge subjected to a uniform electric field. Okay, this charge is nearby the positive plate that is generating the uniform field. That's what the drawing is all about. The charge, this charge is at rest, and nearby, okay, the positive plate that's generating the uniform field. The negative plate is a distance d from the positive plate. Consider a positive electric, so direct to uniform electric field, by the way, E. Okay. Consider a positive electric charge Q. Okay, I gotta tell you what the charge is. Subjected to uniform electric field E. The charge is at rest and nearby the positive plate that's generating the uniform field. The negative plate is a distance d from the positive plate. Okay, find the final velocity of the charge Q, when it is about to collide with the negative plate. Okay, so the situation is like that. Here you go. This positive charge is going to be attracted towards the negative plate due to electric force, Coulomb's law. Not only is going to be attracted towards the negative plate, but this plate also is going to repel this charge, right? So this force here is a linear combination, linear superposition of the repulsive force with the attractive force. Okay, this charge initially is at rest and start accelerating upwards, downwards. What's going to be this final velocity just before it collides with this other plate? That's what this problem is all about. Okay, so we use conservation of potential energy. Okay. So here you go. We have the following equation: initial electric potential energy. I'm gonna, denote by U naught, plus initial kinetic energy. I will denote by KE naught. Is going to be equal, just like we did in in physics 6, right? Is going to be equal to the final potential energy plus the final kinetic energy. Okay. So in this specific case, the electric charge has potential energy. Remember, it's just like the case of the mass in a gravitational field, right? The higher the mass is, the higher the potential energy of the mass. At the ground, the potential energy of the mass is going to be 0. Okay, here also at the ground, which is in this case is the negative plate, the potential energy here is going to be 0 as well. Okay, so here's initial potential energy, here's going to be final potential energy. Oops, 1142. Okay, initial potential energy is going to be what? Just like that equation that we saw before. Initial potential energy is going to be, you know, here you go. Let me get that right here. That's gonna be, you know, that's gonna be my final potential energy. That's gonna be my initial potential energy. So here you go. Yeah, my final potential energy is minus QE XF, which is going to be D. Okay. Let's go. Minus QE XF. By the way, this my XF is my D. My initial kinetic energy is 0. I'm going to specifically state that this is 0 here. My final potential energy is going to be 0 because our mass, once it gets here to this point, is going to be bound to the negative charges, right? And it cannot go anywhere else. It spent all the potential energy. And the negative, find the final velocity of the, okay, I need one more thing here that I didn't give you. Here you go, potential kinetic energy is going to be half of mg squared. Consider a positive electric charge Q of mass m, okay? Mass m subjected to a uniform electric field E. I need the mass of the charge too. It can be a proton, for instance. Okay. And what else? The distance is D. Consequently, my XF, oh, wait a minute, X naught, supposed to be X naught here. Okay. Supposed to be X naught here. Yeah, because it's initial potential. Let's see here. Yeah, it's supposed to be X naught. Okay, this 0 cancels out. I can take this one out, and then we solve for the velocity. It's going to be 2 over m. Okay, and that's going to have a square root as well. And square root, let's get that here. Here you go. And in order to, here you go, V is going to be like that. In order for us to get a real number, right? This X naught is supposed to be minus D, okay? Here you go, like that, minus D, which is the separation of the plates. And then we finally get negative, cancels out with the negative. And that's what's going to be our final velocity of the electron. Okay. So it's 1147. And that's the case of, not the electron, of our electric charge, okay? That is the case of a uniform electric field. Okay, you have to know, in addition to a uniform electric field, you also have to know, in addition to the electric potential of a uniform electric field, you also have to know the potential, the electric potential of a point charge. That's what 19.3 is all about. Okay. Okay, here we go. In the case of the electric potential of a point charge, okay, the V is going to be, that you don't have any choice, that you have to memorize, okay? It's gonna be like KQ over R. In order to derive this thing here, we need calculus, okay? So that's, just remember, just be reminded that the electric field of a point charge is what? KQ over R squared. Okay. In order to go from here to here, all you have to do is take away one of the powers of the R. Okay. Okay. So, and now we can start thinking in terms of equipotential lines, just like we did for our lab, right? So here you go. Going back here for the case of a uniform electric field that I gotta tell you as well, right? For the uniform electric field, there is a relationship between the electric potential and the electric field, okay, which is going to be E times X, okay? Just like you saw in the experiment. The electric potential, must be minus here, right? Don't forget that must be a minus here. E minus E times X. Uniform electric field, right? Electric potential and potential of a point charge. Okay. So if you have a situation like that, the electric potential of this uniform electric field can be denoted by lines that increases linearly. Here you go. Here's one electric potential line, which was okay. And let's say here is the 9 volts, right? The 9 volts equipotential line, and here's the 7 volts. And here's the 5, let's see, 7 volts, 5 volts. Let me put a little bit closer here. That's 9 volts. That's supposed to be 7, that's 5. Okay, now we have it. And then I'm gonna copy all of that. And those are the, okay. Actually, okay, this one is all the way around, right? Remember, the increasing electric potential is contrary to the pointing direction of the electric field. So here you go. So what we have here is going to be V equal to 0 volts. Okay, next, V equal to 1 volt. 1 volt. V equal to 3 volts. 5 volts. 7 volts. And 9 volts. And the last one, in the case of the lab that we had, that was 10 volts. Okay. Like that. Those are the equipotential lines. And for the case of a point charge and a real point charge, let's see if I have an illustration here for you. We're almost there. We have 7 more minutes to go. I have. Yeah, I'll need to do one from scratch. Okay, so here you go. Let me do one from scratch. Equipotentials of a point charge. Equipotential of a point charge. Equipotentials, potential of a point charge. Here you go. If the charge is positive, all you're gonna end up having is circles of electric potential. Field, let's see, no field, good. Yeah, let's see, one more. Yeah, and I'm going to draw some dashes here. If the charge is positive, okay, and then that's one of the key potentials, okay? And the key potential value is decreasing. This curve has one value, this one has another potential value, and that's what you're going to see in our next lab. Okay. So the fields are going to be away from the charge. Okay. And it's going to be normal to the equipotential lines. It's 11:55 right now. Okay, any questions? So let's stop here, and we're going to have office hours right now. If you want to stay around, I'll be available here for you, okay? So I see you again on Monday. And by the way, we're going to have a quiz on Monday. Okay. So I see you on Monday.
All right. Thank you, Professor. So for the quiz, is there anything that we should focus on in particular, or just go over the things that you wrote out or above?
Everything. Yeah, everything from the very first class. Okay.
All right. Thank you.
Welcome.
I'm sorry, one more question about that.
Yeah,
So
go
is it
ahead.
going to be like, are we going to have to work out problems? Is it like a multiple choice? Is it fill in answers? All
Yeah,
of the above?
It's going to be more, qualitative questions, multiple choice qualitative questions. Okay, it can also be some numerical questions, but it's going to be very qualitative, something that you can answer very quickly. Okay.
Okay. All right. Thank you, Professor. Have
Okay.
a great weekend.
You too.